In this lecture, we're going to be looking at the nervous system, and mostly we're going to be looking at the structure of the nervous system, but more importantly, the neuromuscular relationship. So the communication between the central nervous system and the muscles leading to movement. So when we look at the slide here, we can see in the yellow, it's usually the color that the nervous system is depicted in. You can see the central nervous system here, like the brain, spinal cord, and you can see the nerves coming out of the spinal cord and going to the body. But the nervous system is very vast. This is just the small components that we look at, but this includes all the receptors and sensors and other aspects that deal with communication. So the nervous system is divided into two primary systems. You have the central nervous system and the peripheral nervous system. So the central nervous system is over here in purple. You see the brain and the spinal cord. And then from that spinal cord, you have nerves that are coming out, and that's the peripheral nervous system. So that's all the nerves that are coming out to the tissues. And then it's also including, so you have the output, the motor, you have all the sensory aspects. So things coming from your eyes, your taste, your touch, and everything coming in from there. And you have then the motor system divided into two divisions. You have a somatic or voluntary, and that's usually going to the skeletal muscles. And then you have the autonomic, the involuntary things that you normally can't control without thinking about it. So that cardiac muscle, smooth muscle, and everything else. And then what I want to really focus on is the parasympathetic versus sympathetic divisions of this autonomic nervous system. So with this motor or this effect that the output that the body can have, you have the movements here that we talked about quite a bit. And then you have the involuntary aspect, and you have these two divisions, parasympathetic and sympathetic. Now, the sympathetic is probably familiar to you. It's usually referred to as the fight or flight, and these are things that are involved in increasing metabolic output. And so it's deprioritizing digestion, reproduction, repair, because it doesn't really matter if you are going to be able to function in that moment if you are dead. And so these are things that are keeping you alive. So any type of threat, whether it's real or perceived, you have this increase in sympathetic activity, preparing for battle, flight, or trauma. And then the other end of the spectrum, you have the parasympathetic, right? And this is referred to as usually the rest and digest. And so this is going to prioritize metabolic waste removal and digestion and recuperation and repair in times of peace, if you will. And so these two systems are constantly going back and forth. You either have sympathetic input with parasympathetic suppression, or you have parasympathetic stimulus with sympathetic suppression. And you can kind of see in the next slide how that plays out. You can see on the left sympathetic system how it's preparing for battle. Like the pupils are dilating and taking as much eyes as possible. It's taking resources away from digestion, moving them to the musculoskeletal system for movement to move faster and stronger and be more alert and more reaction. And then on the right, the parasympathetic is focusing more on that digestion and detoxification pathway. Now, the sympathetic and parasympathetic nervous systems are driven by the environment, particularly the stress state that someone is in. And stress, as we'll talk about in KIN 231, or we'll talk later in the exercise, the physiological adaptations lecture, that stress is not just mental stress. That stress is physical, chemical, psychic, nutrition, thermal. It's anything that's challenging homeostasis or balance of the body. And these are good things, right? If you're in a low stress environment all the time, you are weak, you are a sissy, you can't handle anything. If you're in a high stress environment all the time and you're not managing appropriately, you are weak because you're sick, damaged, broken, and ready to die. So stress is a good thing and a bad thing, and it all is based on the recuperation. Stress is the agent of change. It's what makes you stronger. If you never put stress on your muscles, they would never have a reason to grow. So it's stress appropriately applied and then appropriate recuperation that is a good thing. And that's really the foundation of this general adaptation syndrome, which we'll talk about again in another lecture. I just want to use it in reference to what we're doing from a fitness perspective, is that if this is your baseline right here, that's homeostasis. Your body's balanced, right? So no increase in parasympathetic or sympathetic. They're equal. And you're exposed to some kind of stress, whether that's self-induced through exercise or through being ill or sick or fall, injury, whatever it may be, that your body then has utilized resources that it's not used to using. Sympathetic nervous system has kicked in, and now you are operating below threshold. And again, if you stay here too long, you end up going down this downward cycle of injury, inflammation, tissue, and damage, and then death. But if that stress then is no longer there, that's what the sympathetic nervous system did, is it neutralized that threat, got you out of there, or you were able to handle it, and now your parasympathetic nervous system kicks in and you've recuperated. If this was strong enough or appropriate enough, your body will overshoot where it was at before, and now you're even bigger, faster, stronger, more resistant to that stress. Now, if you don't do anything, your body reclaims back down to its normal environmental demands, and so this is the process of either gaining resources so you can handle more stress, so you can handle more of this stuff, or losing resources where you can't handle as much of this stuff. And it's a process. And you can see what's happening here is you take like one step back, right? You're actually below threshold of your functional level, and then you take one step to get back to normal and 2 steps forward, so you're at a higher level of operation. And if you impose another stress again, you take 1 step back and 2 steps forward. 1 step back, 2 steps forward. And this is really the process of fitness and exercise, what you want to be the foundation of your programming. So many times people focus so much on the intervention. What do I need to do to work my abs or run faster? And you can see that the intervention is only half or a third of the battle, that the recovery that happens afterwards is just as, if not more important, to your overall progress. So it really is this journey of 1 step back and then 2 steps forward. And then you introduce another stress again, 1 step back and 2 steps forward. And your journey of fitness is this constant progress of 1 step back, 2 steps forward. But you still end up 1 step ahead. And it's a process that's ongoing. And sometimes you can take 1 step back and maybe 2 or 3 steps forward, but you don't want to get in a situation where you're taking 1 step back, 1 step forward, 1 step back, 1 step forward. You're never getting anywhere. Worse yet, 1 or 2 steps back and only 1 step forward, and so you're starting to decline in function. So again, it comes back to this general adaptation syndrome of that 1 step back, 2 steps forward, 1 step back, 2 steps forward. Again, we'll get more into detail of this. You can have too low of a training stimulus. You did something that your body's not really unaccustomed to doing, so it didn't really see any reason to change. And you can do too much, where you've done too much training stimulus, where you've exceeded your body's ability to recuperate. It's really this Goldilocks principle of just right. And this is where the art of training, the understanding your tools, less is more, no pain, no gain, sometimes needs to go away, because you need to really have this not too little, not too much. And this Goldilocks aspect becomes the primary driving force for how we handle fitness. You want to stimulate, not annihilate, and you're looking for that just right component. You want just enough exercise intensity to elicit a change, but you don't want to exceed your body's ability to recuperate. This is all coming back to this sympathetic, parasympathetic play of how much are you in the fight or flight, or how much are you in the rest and digest, right? We are in a sympathetic dominant society, right? Exercise, stress, bright light, stimulants, coffee, caffeine. And parasympathetic is more like the dark, sleep, deep breathing, relaxation, Zen-like state. If you have a client that's lifestyle is very sympathetic driven, your exercise needs to be balanced appropriately. So you're not doing this sympathetic based exercise that's already adding sympathetic load into an oversympathetic person. And you might need to figure out how can you do more parasympathetic type aspect. So we looked at the sympathetic and parasympathetic aspect. We're going to back up just a little bit, and we're going to revisit the sensory versus motor. And the motor, also referred to as efferent, and sensory afferent, they're basically two, they're under part of the peripheral nervous system, but they're basically two parts, two separate nervous systems in underneath the peripheral nervous system. Your motor system is a dedicated pathway, and your sensory is a dedicated pathway. And so you have your inputs coming from the environment through the skin or receptor, through the peripheral nervous system into the central nervous system for integration and processing. And then if a need or if a response is required, it's converting it to motor signaling through the peripheral nervous system at the terminal end at usually the muscles or any part of the effectors. So again, it's this balance between integrating input from the environment and output for reactions or manipulating the environment if need be. Your nerves are like highways, and you have a dedicated motor output and you have a dedicated sensory input. And so you kind of have this setup where this nerve that you see in the body is really two different highways, two different lanes. You have sensory going this direction and motor going this direction, and you can't jump lanes and go here, right? There's a median in the middle, a wall, barrier, and you can't have traffic going in the opposite direction. And so you kind of are set up with this aspect where you have your sensory input coming in, you have this highway, even though this is one nerve, it's just separated here, but when it comes out of the nerve root here, it becomes one nerve, and you have one cable, one track that is input, afferent, and you have another track that's efferent. Now, when we look at both these models, looking at senses, you have your sense of taste, but you also have your sense of touch and vision and hearing. All of these things are communicated via the nervous system through that afferent pathway. You also have, right, you have your sensory aspect in terms of what you touch, and you have different receptors here that are sensitive to sharp, different sensors here, receptors here that are sensitive to heat or cold. And so even though you can take your same part of your skin here, there are different sensors that are sensitive to certain stimuli, and they only get triggered if stimulated. So if you trigger something with hot, your thermal receptors are going to send something back. But if you trigger something with like sharp or dull, it's going to be a different sensor, but it's still going down that same path and then out to that motor neuron. You have your five senses, but you also have a sixth sense, and no, not your ability to read people's minds, but this thing referred to as your kinesthetic awareness or proprioception. Although you see a lot of times the efferent system, the motor system going down to the muscle, you also have signal receptors in the joints and in the muscles that are also sending information back to the nervous system. There are many of these, but the two primary that your book gets into are the muscle spindle and the GTO, the Golgi tendon organ. And if you look up GTO and you put GTO muscle, you still can't get the anatomy aspect. You're going to end up with a muscle car. But the GTO and the muscle spindle are the two most prominent. They are sensory receptors, meaning that they send information back to the brain about the status of the joint or the limb, where it's at in space. And so the muscle spindle, as you can see here, is in the belly of the muscle. It's here within the muscle itself. And then you can see the Golgi tendon organ that it's at more at the end of the muscle, right where the musculotendinous junction is at before when this turns from red to white. And they do different things. The muscle spindle is more focused on length or stretch of the muscle, and that's what it's sending back to the nervous system. And the GTO is looking at total tension, and that's what it's sending back to the nervous system. And now this information goes back to the nervous system, and the brain can do different things with it. But let's hold off on that for a second. So if this is your muscle alignment, right, and we have your muscle fibers and they run parallel to each other, and then here's your musculotendinous junction, you're understanding how these things, the difference between the GTO and the muscle spindle. So the muscle spindle is parallel with the other fibers. The muscle spindle is actually a muscle fiber on its own. It's a slow twitch, small muscle fiber, but it is in line with the rest of the other muscle fibers. The GTO is actually in series. So the muscle spindle is parallel. The GTO is in series. So it's not in the muscle belly at all. It is here in this musculotendinous junction, and it's at the end of the muscle fiber. And again, this is measuring length, so how much stretching or length is happening, and this is measuring how much tension that is there. So if you've ever seen or experienced a knee-jerk reaction or the tendon tap, that's part of this muscle spindle activity, that you hit the hammer right here at the tendon. This basically is rapidly stretching this muscle. That triggers the muscle spindle, and it sends its signal to the spinal cord. Depending upon how intense it is, part of the integration or processing of the central nervous system, it's saying, hey, this is lengthening way too fast. If it continues at that rate, we're going to have some damage. So what we need to do is we need to contract, so you put the brakes on so that muscle doesn't rip at all. And so what it's going to do, it's going to turn on the agonist, the quads, and it's going to turn off the hamstrings, which are going to make them antagonists. So that's the muscle spindle. It's in parallel with the muscle fibers, and it's sensitive to stretching or lengthening. And you can remember spindle, muscle spindle, and think spindle for stretch, so stretching. The GTO is slightly different. Again, it's at the end, it's in series, it's not in the muscle belly itself, and what it's doing is it's monitoring tension. So how much tension is being generated. It's sensitized to a certain threshold, so if it gets to a certain amount of tension, it's going to send its signal to the nervous system, and the nervous system can then integrate it in any way it wants. Depending upon where you're at in your gait cycle and what's happening, it can either turn the muscle off to put the brakes on, or it can keep it on depending upon what else it was signaling. But the GTO, so T for the tendon, monitors tension, and that's how it's triggered. Now, whether it turns things on or turns things off, there's a lot of research that shows that GTO can do both, but the science does show that it's sensitized to tension, and the muscle spindle sensitized to stretching. So again, here's your muscle spindle in the belly of the muscle. Here's your GTO, and I'm sorry, this is your motor neuron. This is the muscle spindle here. Here's your GTO here, your Golgi tendon organ, and it's the afferent information coming up the nervous system into the spinal cord. And then here's your motor neuron doing some kind of response. It's either turning it off if the tension is too high, or triggering it to turn on if it needs to stay on. And then you have your muscle spindle here that's actually in the belly of the muscle, and it is sending its signal based on how rapid or stretching it is, and that's either turning muscles on to protect it, and then turning muscles off so that it can do what it needs to do. So again, that's just showing the different tracks of the afferent sensory input compared to the efferent motor output. And again, these are two different tracks, and you have a highway that's dedicated towards sensory, and you have another highway that's dedicated to motor, and they don't overlap. So what you're seeing here is a picture of a neuron, and this is the basic structure, general shape of the cellular component of the nerves. Now they vary based on location, but they have the same structure. They have this soma, or the body. They have the axon, which is the length of the muscle, or the length of the neuron, and then they have these extensions called dendrites that are coming up, and they're both on the receiving end and on the transmission end. Now, these cells, these can be large, just kind of like the muscle fibers, and some of these cells have axons that can be up to 1 meter long. So these are large cells. Again, another picture of the neuron. You can see the soma, the cell body. This is where the nucleus is at in the life support center. You have the axon, and then you have these terminal branches, or the dendrites. The axon is the think of it as a cable, and it's sending these, sometimes referred to as neural impulses, and the action potentials are really the transmission or the signaling that the nerve is doing. That's what the nerves do, is they're signal transmitters. They send signal through the body for either awareness, like for sensory, for the brain to process and do something about, and then they're sending signals down for the muscles to actually, or the other connective tissues or other tissues to do their job. This action potential has a very specific direction of flow. So the information flows from the head to tail and never from tail to head. So there's a very specific direction. But this action potential is really a depolarization, repolarization current. It's usually depicted like this. And it's basically, what I want you to visualize is, this is the most important aspect of this slide, are these arrows that are jumping down. These little gray circles are meant to represent myelin, and the myelin is an insulator to help that signal propagate all the way down. And the signal for nerves is usually referred to as like an electrical signal, right? Where you have like if you look at this as a nerve, this is your sensory and this is your motor, and like an electric current coming down. But it's not quite electric current. Electricity travels almost 3 million times faster than how fast the neural communications happen. And neural signals traveling between 2 to 180 miles per hour. So really fast, but not nearly as fast as electricity. It's still electrical aspect because there's a gradient or chemical gradient that's occurring. And so you have these polar opposites of like positive versus negative. And what this is really is it's a chemical signal that is using electrical current, but it's repeating, and you're not getting any signal loss. So with electricity, you get signal loss, but with this chemical transmission, there's virtually no signal loss with neural conduction. So it's a little slower, but significantly more reliable. And so, you have this particular impulse, this action potential, and you can see it's like a wave of like positive, negative, positive, and it's going all the way down, and it's propagating down. So it's like this wave that's going down, this depolarization where it's positive, negative. So it's like an electric current, and it is kind of like a wave that you see at a sporting event. So if we look at this wave here, no one's transferring anything to anybody. They're just waiting for the first row to do their thing, followed by the next row and next row and next row, all the way on, and it's just propagating all the way down. And this is how action potentials are working within the nerve. It's just a depolarization wave that's coming all the way down, a chemical signal transmitting a electrical output at the end. So again, you want to think of the action potential as this wave-like form. And what's really interesting is that this is communicating nothing more than, am I on or am I off? And it's looking at this binary code. And so you're getting this 0 and 1, or on and off, or stop, go in your communication, right? That's it. It's just a series of on, off, on, off, on, off. And that is how all of your sensory and motor communication is happening in the nervous system. So everything that you can taste, everything you can touch, everything you can see is nothing more than a series of 0 and 1s being sent up these nerves, and then your brain is integrating that. So when you see the color blue, it's nothing more than receptors that are falling on your eyes that are triggering then certain sensitive tissues that are sending 0, 0, 0, 1, 1, 1, 1, 1, 1, 1. And that's how you are seeing blue. Or when you hear certain sounds, or when you taste certain things, it's mind-boggling when you think of how the body actually operates. So what we talked about with action potentials are the propagation of the signal in the neuron itself, but now what we're going to talk about is how do neurons communicate with other neurons or other tissues. And what's interesting is that neurons touch nothing. They're floating in space, and all nerves have a gap that's between them. And this gap is referred to as the synapse, and the synapse is that junction here. That action potential still continues on, so you're seeing action potential going down the neuron, and it's hitting this other neuron, and what you're seeing is a blown up picture of this synaptic gap. The thing to appreciate in this slide is that you have these vesicles of neurotransmitters, and when that action potential reaches the end of that dendrite at the terminal end here, it triggers the release of these neurotransmitters, and it's the neurotransmitters that jump the gap, and that's what is the next domino in the line that is sending that signal on. So the action potential repeats, and there's again no loss of signal because it's repeating with each chemical release, each depolarization. So within the cell, it's an electrical current that's kind of going down, chemical that's depolarizing, and then when you get from neuron to neuron or neuron to other receiving tissue, it's a neurotransmitter that is basically transmitting that neurosignal onto the next tissue. With the muscle, you have this view here. Instead of receiving onto another nerve, it's terminating with the muscle itself. And in this case, if you're sending a signal down the nervous system, the nerve can either be signaling a go or nothing at all. So it's either getting a go or a stop. And if the go signal is coming down the nerve and it's going to the muscle, it has only one intention, and that is to generate tension. That's it. So if I'm getting this go signal down the nervous system, that action potential, that means it's starting the process of muscle contraction. And so when we look here, same thing, the neuron does not touch the muscle fiber. There's a gap there. And this is called the neuromuscular junction. So you have the neuromuscular junction, the synapse, and you have certain neurotransmitters here, acetylcholine, that are waiting to send its signal. If that action potential is coming down, it's sending its signal down, and then if on the video that we had on the sliding filament theory, it starts that whole process of contraction where you have the neuron sending the acetylcholine that's going down into the T-tubules, that's forcing the sarcoplasmic reticulum to release calcium, and then you start the whole binding process with calcium so you can get that cross bridge formation. So if this is new to you, definitely watch that video in the muscular unit that's talking about sliding filament theory and neuromuscular contraction.